Okay, so we're starting a new unit, Unit D, where we're going to actually start doing some of the simulations. We're going to start out using Microsoft Excel or Google Sheets, and then just to sort of we can see what's going on behind the scenes, and then we will introduce Vensim and Insight Maker, and you'll do some pretty simple simulations of things like toilet tanks filling up and bacterial growth and those sorts of things. And that will set us up for the midterm. And then after the midterm, we'll start doing more complex sims and case studies and so on. So um, let's get into it. So dynamical systems, word dynamic here. This is systems that change over time. So, these behavior over time plots, it's all about, these are things associated with dynamical or dynamic systems. And dynamics really have to do with the forces that stimulate growth, development, or change. So that's what in our models, we're effectively putting the forces that are causing change and letting the computer generate the changes for us. So we can take kind of two perspectives when we think about dynamical systems. So like a curve like this or behavior over time plot like this one here, we can take the kind of more conventional perspective where we actually write a function that plots out for every time what is the system doing. So this makes it very easy to predict values because we can sort of say, well, for any particular time, we just evaluate this thing and we immediately know what's going on in the system. That's one perspective, but it doesn't tell us a lot about what's driving the system. So then there's this other perspective that looks more calculus-based, where instead of just simply focusing on where the object is, we try to focus on how rates of change relate to each other. So this was the perspective that when, say, Isaac Newton, looked up into the sky and saw planets orbiting around and sort of asking like, well, I know simply knowing where the planet is at any particular day is this perspective, but trying to understand how it moves through this orbit requires a different type of perspective where we need to relate velocity, position, and acceleration. And that's kind of this perspective here, where we've got rates of change. And by writing things in terms of rates of change, it illuminates a kind of causal web in the system. So I've written this, this expression here, and I claim, but it's kind of outside of the scope of this class, but in like a, kind of Calc 211, or sorry, SOS 211 type logic, that this perspective, where I've got the change in y over time is equal to x, and the change in x over time is equal to this expression times y, this I claim, if you were to solve that, so if you were to sort of solve for y over time, it would give you exactly the same thing. And so if you would like to try that, sort of an at-home exercise, you could take this, this y function here and take its derivative with respect to time. And I think you'd find that what you would get out is another thing that you could call x. And then if you took that x and took it with respect to time, you would find that what you'd get out would be exactly the same thing here times this factor. So just taking two derivatives of this thing will give you this thing over here. So why is this thing better? Well, if I look at this expression, I can sort of extract a causal loop diagram, and I can see that these two variables I've created, x and y, they influence each other. X has a positive influence on y, and y a negative influence on x. And once I see that, I'm like, oh, that's a balancing loop. And I know that balancing loops with delay can produce oscillations. So it sort of now makes sense that I'm getting this oscillation because inherently this system, if I model it this way, has a balancing loop, and for reasons that are more complex, technically even a balancing loop with delay embedded within it. So this perspective, this kind of calculus perspective, helps us see those dynamical forces. And that's what we kind of, that's what we're modeling in. When we hit play in our simulations, we get effectively this out, but we do the programming with this perspective over here. That's kind of where we're going. And so that's not supposed to make total sense. It's sort of a high level picture of that we're used to looking at behavior over time with this perspective. So plot this thing, you get that. But we're trying to develop a perspective where we don't care so much about where it is at any particular time, but how different aspects of the system relate to each other at all times. And there are sort of easier ways for me to motivate this. And so I can go and think about not something so crazy as, planets orbiting the sun, but I can think of instead compound interest at the bank. So in compound interest, I put $10 in a savings account. Let's say it's a really good savings account. So, 20% interest as opposed to, 0.20% interest and compounded annually. So, what that means is that I can apply this so-called compound interest formula. And that formula is something you learn in like a basic, finance class or, personal accounting, some sort of thing like that, is that, the compound interest formula takes your initial deposit, and it's got a formula here where from your initial deposit and the interest rate, if you put the number of compounding periods in this exponent, you can choose for any year out or any compounding period out from your initial deposit, you can figure out how much money is going to be in the bank. And so this is just a formula you kind of learn, and you could plot it. So you could say at year 0, I have $10 in the bank. At year 1, because it's compounded annually, I've got whatever, 12, and so on and so forth. And you get this kind of growing curve here. And so that's one perspective. But the problem with this compound interest formula is it's hard to figure out what's going on year to year. Like if I were to just give you this formula and say, this is going to describe your money from year to year to year, you might be able to squint at it and kind of tell what's going on, but it doesn't immediately make it clear what exactly are the fundamental forces that relate one year to another. This is how your initial deposit relates to any other year, but it doesn't tell me how my amount of money one year relates to the amount of money the next year. So this is one perspective, but I could take a different perspective where I could say, well, let's think about the system. I make an initial deposit, and then I calculate interest from that initial deposit, and that's just 20% times whatever the initial deposit was. And then from there, so I can think of this in terms of a causal loop diagram. The bigger my balance, the bigger my interest. And then from there, I can add whatever that interest was to the previous year's balance, and that gives me the next year's balance. And from that, I then can iterate through this process where the next year's balance gets, 20% of it will get added to it, and that'll give me the next year's balance, and so on and so forth. And so as my interest gets bigger, my balance in the next year gets bigger, and I get a reinforcing loop. And so if I look at this here, this is the expression that I've modeled with that little diagram. Next year's balance is this year's balance plus 20% of this year's balance. So that really tells me how compound interest works from year to year to year. It's just 20% of the previous year. The problem or the downside of this, sort of clarified perspective is that in order for me to figure out what my balance is going to be 10 years down the line, then I have to actually run this 10 times. I have to start with my initial, figure out what it is going to be in a year 1, and then iterate. Year 1, put in here, figure out what's going to be year 2 in here, year 3, and that I'll end up getting the same plot as I had in the compound interest formula, but instead of immediately being able to calculate year 10, I have to calculate years 1 through 9 and then year 10. So it takes longer for me to get there. But if you just told me how compound interest works, they just add 20% of your previous balance to your balance every year. This captures that. So this captures the dynamical forces driving the interest process, but it makes it harder for us to figure out what your money is going to be several compounding periods out, and that's why we have to simulate the bank. So that's kind of the two perspectives that we have here. And I just realized I didn't log into the poll everywhere, so that's what I'm going to do that real quick. So are there any questions about compound interest? So I use compound interest because once upon a time, it was something that I think everybody had like in high school or something, but for whatever reason, I feel like there's a lot less of that kind of like, the personal finance type stuff. So if you have questions about compound interest, it's weird. I used to use compound interest to help explain bacterial growth, but now I feel like a lot of students come in knowing more about bacteria than money. So so I feel like I need to switch these. But so that everything that makes sense so far. Okay, I've got a rogue mouse here. Let me see if I can. Okay, there, good. All right, so I want to show that graphically. I'm going to kind of start introducing this kind of liquid analogies here. So, and we'll see why I do that as we get further along here. So the idea here is I put in $1 now. That's my bank balance. I'm going to call that a stock. So a stock is, it's a state variable. It changes over time. So this is my initial stock here. And every year I calculate interest that I don't get this year. I get next year, but I know how much I'm going to get next year. So I know that if I have $1 all year, the next year 20 cents will be added to it, 20 to 20% times $1. So that's my generated interest. So it's as if this dollar is reproducing a fractional dollar that ends up reaching maturity and being able to reproduce itself the next year. So in the next year, this is my stock now is 1 plus the 20 cents. And then each one of those reproduces 20% of itself. So it's like they have a reproduction rate where this dollar produces another 20 cents, but then this 20 cents produces whatever 4 cents. But then these two, I don't have access to them anytime this year, but I'll get all 4 of these boxes the next year. And that's kind of a graphical depiction. And then all 4 of these end up reproducing 20% of themselves. And then that's how the compound interest is kind of working sort of graphically. So that's how we can think about the bank model. And if I were to then plot these, I start out with $10 in year 1. I go up to $12 in year 2, $14.40 in year 3, and I could keep doing that, and I'll end up getting that exact same kind of growth curve that we had before. So that's how we do that. So that's graphically how we do it. Of course, we would normally do it in something like a spreadsheet. So I'm introducing this because we're going to make minor modifications to this to simulate any dynamical system. So if we understand how compound interest works, we can actually understand what Vensim and Insight Maker are doing behind the scenes when you ask them to simulate any system. So this isn't all about just balancing a checkbook or something like that. All right, so like if I were to go into Excel, I could create a little interest rate column or interest rate cell here. And then I could say, I want to simulate my bank account through all of these years. So now in each row, I have to put in formulas which relate the balance in each row to the balance in previous rows. So I put my initial balance in 10. I know my interest earned is just going to be this cell B4 times the interest rate. Now, how many people have used the dollar signs in a spreadsheet program before? Is this a new concept? Is anybody familiar with the dollar signs? Okay, so for those unfamiliar, it's just for everybody online too. There are very few hands who are familiar with the dollar sign. So if you're unfamiliar, totally in welcome company here. So the idea here is that if you were to take this cell, an ASTIC cell, to fill this formula down, if you don't anchor it with a dollar sign, it will either change the letter, which is the column, or the number, which is the row. So if I pull this down, I'm keeping everything in the column, so it'll keep the B. But if I pull this down, that B4 is going to turn into a B5 in this cell, a B6 in this cell. By putting the dollar sign in front, that's telling you that no, I don't want that to change. I want this to be 1 in all of the cells. And so because interest rate is what we call a parameter, an exogenous parameter, all of the cells will refer to B1. So anything I put up here, any auxiliary variables that I put up here, I'm going to need to anchor them. And I usually just put dollar signs in front of both so that if I drag them to the left or right or up and down, Excel doesn't, or Google Sheets doesn't change those numbers. So that's why there's not one there, because when I fill this down, I do want the B4 to become B5, B6, or whatever. But with these, I want the B1 to stay B1, regardless of where this is. So any questions about those dollar signs there? How the dollars work in these spreadsheet programs? including questions online. That makes sense. Okay, so that will calculate my interest at the end of year one. And then to calculate year two, then I just take previous balance and I add the interest from the previous year. And those are really all, that's all the math I need to implement this. And then if I drag, so in Excel, I can drag this little, notice this corner is a little bit different. If I take that corner and drag it down, or the corner up here and drag it down, or you can highlight, starting with this thing, highlight down, and you can say fill down, and there's hotkeys you can use as well. But if I do that, then it'll take the formulas that I put here, and it'll copy them down so that I end up getting a balance that grows and an interest that grows. And that's how I simulate my bank account balance. And I can go and plot that. So if I did this in Excel, I can highlight the year in the balance columns. I can go up to the insert tab. I can go over to these graphs here, even recommended charts. And what I like to do with these is choose a scatter plot, and it will then scatter year on the x-axis and balance on the y-axis. And the result will end up being exactly the same plot that I had before. So that's a way to get to that. So that shows that by modeling what happens from year to year to year, we can have Excel simulate what happens over multiple years, so that even though we don't have the compound interest formula, we just have the year-to-year formula, it can give us the same outputs. And that's effectively exactly what we do in simulation. We're going to model what happens from instant to instant in a system and let our Vensim or Insight Maker do what Excel did here and give us the ability to simulate, all right, well, if we know what happens from instant to instant, what happens after 10 minutes? What happens after 10 years? And it'll do all of those little instants just the same way it's doing all of those little compound periods. So before we get into this thing, more complex examples, are there questions about this example here about the compound interest? That by modeling what happens from year to year, we can get the same plot that we get out of the compound interest formula, which models what happens in every year. Okay. Questions online? All right. So this was a specific case. We can think more generically that what the form that we have here is in any one of these types of systems that we're trying to simulate, we have time steps. So we have a clock that we have to sort of keep track of in one column. And then we're going to have a set of stock variables. Balance was our stock variable in this particular case. And these are sort of state variables. They're the things that change over time. But we don't know how they got there when we started the sim. So the key thing about all state variables or all stocks is that in the first row, we have to put their initial condition. So stock variables always have an initial condition, which is not a formula. So in the balancing, it was your initial balance. And then every other row for a stock is going to be a formula, which is based on their previous value and the values of things in this sort of previous row here. So we also had this interest earned column, and that's what we're going to generically call a converter variable. It's a weird term, but it basically is just an auxiliary variable to help with calculations. So we didn't necessarily need the interest earned formula. We could have put everything in the balance column here, but it was convenient for us to calculate interest in the same row as the balance and then use it to generate the next year's balance. So it would just visually and presenting it to others, it was just easier to break those apart. And so those converters are these things that help us convert quantities. So if we know whatever the stock values were in this row, we can convert them to other quantities that will be more useful in calculations of the future stock values. That's why we call them converters. So in our generic example, again, balance is a stock, interest earned is a converter. Balance is a state variable, it changes over time. Interest earned is a function of state variables. Its value is totally dependent upon the other state variables. So any questions about those terms, stock and converter? We see the qualitative difference. Converters are all formulas, even in the first row. Stocks have initial conditions, which are not formulas, and everything else is a formula. Questions online? All right. Everybody good. Okay. All right, so now that was our cute compound interest model formula here, but we'd like to, we talk about populations and so on. So we'd like to be able to see if we can take the same logic and use it to simulate something like a bacterial population, bacterial growth population. So we have to think about what are the analogies here? Well, how do dollar bills reproduce in a savings account? Well, they reproduce by interest, so that's very different than how bacterial cells reproduce, but is there a way we can create an interest analog for bacteria? If there is, maybe we can simulate. So that's kind of the key point here, is that bacteria are not dollar bills in a bank, but we don't know how to simulate bacteria. So if we can come up with an analogy that's mathematically sound, that maps bacterial growth to bank growth, compound interest, then we can take all of our insights from compound interest and use it to simulate bacteria. And so basically what we're getting at here is, if I look at bacteria at a small enough time scale, it turns out that they operate just like interest in a bank. In other words, everything looks like a line if you zoom in on it. So regardless of what curve that you draw, even lightning coming down from the sky, if you zoom in on a small enough portion of it, at some point, it's not going to look like a curve, it's going to look like a line. And that's what we take advantage of, is that even though bacteria do not grow like dollar bills, if we zoom in on them and only consider them for very small instants of time, we can pretend like they do. And as long as we use small instants over and over and over again, then our bank model will work just as well for the bacterial model. So that's what we present today. So let's think about bacteria here. How do bacteria reproduce? Well, there's no compounding period in a bacterial bank. Instead, we can think about, what does the average bacterium do? Well, it's got some waiting time that I'm calling W. I use W just for no good reason other than it's how long we wait. So each bacterium reproduces itself after an average of W waiting time. So some bacteria take longer than W to pop out a new bacteria. Some take shorter than W to pop out a new bacteria. They do not synchronize their reproduction, unlike dollar bills. So some bacteria are going to reproduce now, others later. It's not like there's one period where all the bacteria reproduce at once. And each bacteria doesn't produce a fractional copy of itself like a dollar bill. They produce a whole new bacteria. So that's the challenge. We need this to be turned into a bank model for us to be able to simulate it. So we're going to try to approximate bacteria as if they were a bank. And what do we need to do that? Well, for one, we're going to, again, we're simulating the average bacteria. So we're going to say, what if bacteria, we know they're not doing this, but because we're averaging over time, what if we picture bacteria as constantly oozing out a small bit of new bacteria at some slow rate? If we say that they're oozing out new bacteria at a rate of 1 divided by W, then what that lets us do is, after W time, each bacteria will have 2 bacteria. So it's like an analog clock is right, a broken analog clock is right twice a day. It's kind of the same idea here, where we if we do this right, it's going to give us sort of the wrong population, but it's going to hover around the right population, and it'll be instantly right at small periods. So it's like, have the right number, we'll start with the right number of bacteria, and then they'll ooze out slowly. So during that period, the real bacteria aren't reproducing, but the fake bacteria are getting fractional bacteria added in next to them. And after W units of time, then all of these oozings, like if I multiply the slow rate times W, gives me a new 1 bacteria. So if I go out W, then I'm going to have an average 1 bacteria per bacteria added to the population, the same way I would if they were reproducing, sort of the normal way bacteria reproduce. The other thing I have to do is say, well, how do I synchronize their reproduction? Well, I've already kind of gone halfway there with this oozing model. So the idea here is that I'm not going to allow I'm going to have to zoom in on small time period that I'm going to call dt. So I call it dt. Vensim calls it time step. I think Insight Maker might also call it time step. And so the idea here is we're going to just look at a very, very tiny, a millisecond, and we say how many bacteria are at the start of that millisecond and at the end of that millisecond. Now, in the real world, there would be no change in bacteria every millisecond or whatever, because it would be very rare. And if there was any change, it would just go up by 1 or 2. So we make it so small that in the real world, it would be very unlikely for there to be more than one bacteria to be popped out. And if we have it that small, then we combine that with our oozing model here. And what we're basically saying is every dt, we add, like interest, a little dt times this rate, 1 over w bacterium at everyone. So it's like the interest rate here is the length dt times 1 over w flow. So that's kind of how we end up turning this into a bank model, is that this, we create an interest rate, which is sort of like every bacteria adds an average of dt over w new bacteria every dt time period. And as long as we make dt really, really small, then this bank balance should be very close to the average number of bacteria you would get in a real population, like up here. So this may still be a little fuzzy, but I think when let's walk through an example, and I think it'll start making a little bit more sense. So, so again, that point down here, this dt has to be much smaller than w. So dt divided by w has to be much smaller than 1. So the time period, the time step that we're simulating has to be way smaller than the duration of the fastest event in our system. So in this case, the fastest event is the waiting time between reproduction events. So we need dt to be much smaller than that waiting time in order for this to work. All right, so let's see what I mean by that. So this is our real system. So one bacteria waits on average w time to produce 2 whole bacteria. We're approximating it by this system. One bacteria is always oozing out slightly more new bacteria at a rate of 1 divided by w. So this is how much, again, it's like a faucet being turned on at this slow rate. After w time units, this flow would fill this bucket. So this bucket is like a whole bacteria tall. But we are only going to simulate a very small amount of time. And so the new bucket, which is kind of like our interest rate per dollar bill, so this is like the amount added per dollar bill, is going to be this small amount dt times the flow rate 1 over w. And that gives us a very tiny amount of new bacteria added per time step. And then in the next time step, this small amount of bacteria is going to get its own chance to ooze out. And that's kind of the key here. So we can't make dt too large, or else we lose the opportunity for potential bacteria to start reproducing themselves. And so that's what we'll see here in a second. So we need this dt to be very small, is what I'm saying here. So the way that looks is we've got a stock of bacteria, our population of bacteria. Let's say there's 1 of them. And then we have this 1 over w is what we're calling a flow. So we had interest rate, which was kind of related to this, but the interest rate in the bank is what we refer to as the flow times the time interval. We split those things up and we say the flow here is how much we're sort of assuming that every bacteria is oozing out per unit time. And then we choose a small time step where we multiply that flow times the small time step, and that gives us our generated interest in our simulated bank account. So then we have our bank balance as our stock plus the interest, and we just move forward with exactly the same compound interest idea. We've got 1 bacteria produces a fraction. That fraction does not start producing until after the compound period. And then after the compound period, both the bacteria and its fraction start reproducing, but their reproductions aren't going to be start reproducing themselves after the next compound period, and so on. Exactly the same as we did with the bank here. And so we can say we start with one bacteria, we get one plus a small bit, and then we get that small bit plus another small bit, and so on and so forth. And so we can predict that. And if we do that over lots and lots of time periods, then we end up getting what hopefully starts looking like an exponential growth curve down here. And so if dt is very small, the downside of this process is that this simulation will take a very long time to run. But if dt is very large, then this won't look very much like an exponential. It'll look kind of much slower, and it'll be very different than the real system. So our challenge when we build our systems is to set this compounding period small enough to be a good approximation of reality, but large enough to not cause Vensim to take years to finish its sim. Yeah. Well, the dt is what I'm saying is the milliseconds. The w is the waiting time between events. And so you can think of the 1 over w as a rate of new, this you can think of this as how many per bacteria, how many new bacteria are generated. We're saying there's one bacteria generated per w time. That w time could be a year. And so we're saying that on average, there is an outflow from every bacteria of one bacteria per year. And they say, well, then how many bacteria are created not in a year, but in a millisecond? Well, it's a millisecond times that. Any other questions about that? All right. Questions online? Yeah. Yeah. Well, so the idea here, it's a great question. So why does this time interval have to be small? And the idea here is, let's say I made dt large, like 10 years. So it turns out that if I have 5 bacteria today, and I want to figure out how many bacteria I'm going to have in the petri dish in 10 years, I can't easily figure that out just by knowing how many I have today. So rather than sort of saying, can I jump immediately from today to 10 years? I have to go down and say, all right, if I have 5 bacteria on average right now, then how about how many bacteria do I have in the next minute? And then after that minute, those bacteria start reproducing. So if I immediately try to go from thought, like if I said these are got an outflow of whatever this rate is, and then multiply that by 10 years, I'm going to undercount how many I actually need in 10 years, because all of the bacteria that would have been generated in between there wouldn't be included in my model of reproduction. So I have to make dt really small, because all those tiny little bacteria that only exist on average need an opportunity to reproduce. So I need time steps because the computer has to calculate, things in discrete jumps, but I need to make the jumps small so that I don't skip. That's why I need to make this dt much smaller than the reproduction time, because the hope is that I don't jump over a lot of reproductions, because any reproductions I skip in this process are ones that could also be contributing to the growth. Does that make sense? Any other questions about that? That was a great question. Yeah. Yeah, but you won't have. So what you're going to do is in Vensim, you're going to specify in Vensim or Insight Maker a flow rate for every state variable. So you're going to say, I want to model the number of people who are susceptible, infectious, recovered. I want to model the number of people who are recycling or not recycling or whatever on average. And then I want to say, how does the number of people who don't recycle affect the growth of people who recycle and vice versa? So I'll write a flow equation for that. And then in Vensim or Insight Maker, I will, in a separate part of the model, say, I'm allowing you to move forward at a time step of 1 day. And so that would say that if we know how many people are recycling on Monday, we're going to be able to guess how many people are going to recycling on Tuesday. Now, Tuesday will have a different number of people recycling. So then if we know how many people are recycling on Tuesday, you can guess Wednesday. Now, you might say, well, this is really slow because if I want to simulate a whole year, then Vensim has to do 365 calculations. So I could say, all right, what if I do it by month? I'm going to say, okay, Vensim, I'm going to tell you how many people are recycling on January 1st, and I'll let you go in month steps. And then Vensim will move a lot faster. So over a whole year, it only has to do 12 calculations. But if it turns out that the churn of people recycling happens at a much smaller time scale than a month, then you're going to skip a bunch of dynamics. If it turns out that actually whoever is recycling on January 1st is probably the same people recycling on January 31st, then in that case, there's no reason to simulate a day-by-day scale because those state variables aren't really going to change. So that's kind of, it's going to be hard because what you're basically going to do, and we're going to see this in this unit, is that you're going to run sims at different time scales, and eventually you'll get a time step where kind of the graphs, the behavior over time graphs stop changing. So you'll do like a year and then like a month, and there'll be a huge difference in behavior over time. And then you'll do a month and then a week, and there'll be a little difference. And then you go a week and a day, and the behavior over time looks the same. And at that point, you can say, well, if I can do a week and a day and they both look the same, I might as well do a week because my sims finish faster. Does that make sense? Sort of? Okay. Any other questions? So how does this relate to calculus? Well, if we think about our stock now and our stock 1 dt later, and we say, well, 1 dt later, it's just whatever the stock was now, plus whatever that flow equation was, times this dt distance here. Well, this starts to look like the legs of a triangle. So if I put a triangle there, hypotenuse of a triangle here, then I've got, I've got a slope. So this is like, if I would call this the stock function, and this is like the stock function at some time later, then this is like estimating the slope from one point to another. Well, if you think about it, the slope is rise over run. So if I do the rise here, flow times dt divided by the run, which is dt, I just get the flow out. So what effectively we're saying here is these flow equations, like the 1 over w, those are the derivatives of the stock. And if you make the dt really small, then you know that, like, if you're plotting a function. So let's see if this works. I think I can annotate on the screen now. Let me make sure I'm co-host. Oh, there it is. So if if I have a function over time, at a particular point, I could plot a derivative, which would be the instantaneous slope at that point. Well, we know that if I were to instead pick 2 points, like here and maybe down here, maybe I'll put those in different colors, like yellow here, and down here. And if I were to connect those 2 points, then as those 2 points, the yellow points, get closer and closer together around the red point, then this chord, that forms, the slope of this chord, the yellow line here, becomes the same slope as the derivative. And so that's really all we're saying here, is that we're going to write formulas that represent the derivative of our stocks, but our computers can't do calculus, like raw calculus, analytical calculus. All they can do is this approximation where instead of assuming a derivative exists at a point, to a computer, a derivative is the slope between 2 points. And so in order for us to make those two things kind of close together, we need to make sure that our 2 points are close together. So that's what's happening, is we're making just like as you let the limit as the point, like if you've got 2 points and you let the limit of the slope as their distance become close together, that becomes the derivative. It's the same thing happening here. In order for us to approximate a differential equation with a computer that can't do math, we have to actually assume every derivative is actually the slope between 2 points. And the only way that approximation works is if those 2 points are really close together. And so this is us just taking the limit as x or delta x or however it was taught to you, as that goes to 0. That's us saying that we're taking this dt and we're getting as close to 0 as we can, without it getting so small that the computer has to spend an infinite amount of time doing our sims. So, but again, this is kind of, it's getting a little abstract, and so the goal here is not to have like a super detailed knowledge of what's going on, but we at least need to know like what the hell's a time step, you know? Because you need to set that in Vensim and Insight Maker. That's, I'm just trying to give you a little bit of background to see where this notion of time step comes from. So I lost my mouse, I think. There we go. So that's all I'm saying. As dt becomes small, the approximation slope becomes equal to the derivative. And so this is how a flow relates to a stock. The rate of change, the change in a stock over time is equal to its flow. So we want to make dt small so that this slope is approximately this equation. So this is what we're going to write math for, and this is what the computer is going to do. To make them similar, we have to make the dt small. Okay. All right, so let's do an example then with the bacterial simulation that looks a lot like the compound interest. So as with the, oh, I got a question online. So would you say that this is analogous to the fidelity rate of digital music based on sample rate? And I'd say there is an analogy there as you sample music faster, but that's a little bit more complicated because it has to do with redundant information. So in the case of acoustics, there's a lot of redundant information, and so because things can only change so fast, and so you only have to sample at a certain rate in order to recapture all of the information. If you sample any faster, you're not gaining any information. And that is sort of related here, because if you make the dt smaller and smaller and smaller, it's just a waste of effort. But the math behind it all is slightly different. But I definitely think it's a good sort of conceptual model there, is that how do we choose, you know, just like you don't need to put a whole bunch of data in an MP3 if the acoustics don't change that much. We don't need to put a whole bunch of simulation time steps into a sim if the bacteria don't change that much. So there's definitely a conceptual relationship there, sure. All right, so if we want to simulate our bacterial population as if they're compound interest, in the compound interest thing, we created a parameter called interest rate. So here we break that interest rate up into 2 parts, and it's going to be this dt, which is our time period, which is our compounding period, and this w, which is again the time in between reproduction events. And so you can think of this, if our time unit is seconds, then this would be 3/4 of a second. So I could have done 1 over w, and then I would do 1 over 0.75 here, but I chose to use w. And you can imagine putting notations here as well, like just to make it easier to read. Like this would be the average time in between reproduction. I could have done something like that. I list this caveat here that because dt it's lower than w, but it's not that much lower, it's probably too large. So we really need dt to be approximately 0. So we need dt divided by w, or dt divided by the fastest thing that could happen in the system. We need that to be almost negligible. It has to be something in order for the computer to move, but we want it to be like 0.0001 or something like that. But I can't tell you exactly how big it has to be, because it depends on how kind of well-behaved the system is. So, but this is probably too big because it's sort of on the order of the same size as W. All right, so then once we've got, this is all we need for our interest rate. So now we set this up like the bank. Time 0, initial condition, 1 bacterium, flow of new bacteria. Okay, so this flow here has got 1 divided by B2. That's my 1 over W right there. And I'm going to take that 1 over W and I'm going to multiply it by the number of bacteria. So this isn't the full amount of interest because I haven't multiplied by dt, but it is the flow here. So it's the contribution. It's I've got this much bacteria is flowing out per bacteria. So I multiply this times the number of bacteria. This is how much is flowing out of the whole population at this time. So what I then do with that, and so this is me sort of equating this to calculus here. So if bacteria are my stock, then if I were to say the derivative of stock with respect to time is the flow, then I'm saying this is the derivative here. So by writing this formula here, what I'm effectively doing is writing this equation down here, where B is the number of bacteria, dB dt is equal to B times 1 divided by W. That's all that I'm writing here. And so what this simulation is going to do is effectively solve this for B as a function of time. But we're, if we were in 211, we might try to actually solve this using integrals, but we're not in 211. We'll let the computer do that. So all we have to do is just write the equation. That's what we're doing here, and let the computer do the solution. So how do we do that? Well, we go to the next time step, and that's just the previous time step plus dt. So this were number of compounding periods before. Now it's time in the future, where we only move a tenth of a second or a tenth of a time unit into the future each time. So that's why it's the previous time plus that one. And then for number of bacteria, it's similar. It's the previous number of bacteria plus C5, well, that's the flow of new bacteria times the time. So every unit of time, the previous population produces this many new bacteria. Well, we've only gone a dt unit of time in the future. So we're going to take this, multiply it by dt, and that'll tell us how many new bacteria are added per unit time. Or sorry, not per unit time, per this time right here, 0.1 seconds. And those two formulas, that's all we need to solve this equation. So I can just fill these ones down. So before I do that, are there questions about these two formulas? Questions online? Okay, so if I fill those all down, all three columns, then I get time that marches in steps of 0.1, which come from up here. I get number of bacteria that grow, and I get flow of new bacteria that also grows with the number of bacteria. And if I plot that, where I plot time on the x-axis, number of bacteria on the y, I get an exponential growth curve as expected. If I make this dt larger, then this thing's going to look a little bit more linear. If I make this dt smaller, then it'll fill in the gaps. It'll probably still look exponential, but it'll have more dots here. So it'll kind of curve a little bit more. Right now, you can kind of think of this as being a flat line, a flat line, a flat line. And if I stand far enough away, it looks like a curve. But if I zoom in, it looks like a bunch of links that are just that are sort of approximating a curve. And that right there, if I were to take this and use calculus methods, the solution to this is a function that is proportional to e to the t over w. If I plot e to the t over w, I get the curve that matches those points. So questions about that? How do we feel about that? Yeah. Yeah. So the flow of new bacteria, if I go back to that formula here, then we have to say is I need to know what kind of going from backwards, from the end towards the beginning here, for this dB dt. So that's B is the number of bacteria at any unit time, at any time. In order for me to figure out how that's changing over time, I need to know what's the rate of bacterial production. So the rate of bacterial production is like, there's 5 bacteria being produced every second. And so that's what I kind of need to know here is how many bacteria are produced every second. Well, I said, well, how do I figure that out? Well, every bacteria reproduces 1 on average every W time units. So the 1 over W is the contribution from one bacteria. I multiply that by all the bacteria, and this is how the population is growing. And so this gives me a rate, bacteria per time, that shows how this is growing over time. Does that make sense? I would say it's the instantaneous rate of change of the bacteria population at this time instant, at time 0. And so if I go to this next one that we can see here, like this is the bacterial population. So at time 0, it's at 1. At time 1.3, it's all the way up to 5. And notice that it's shallower here than it is here. So this column is the slope at each one of these points. Yeah. That's right. Yep. Yep. Yeah. So I made that a $, so that when I pull that down, it'll stay B1. Similarly, up here, $, so when I pull this down, that stays B2. All right. Other questions? Okay. Good. Okay. So generically, the way all of these, if you were to generate a system dynamics model and manually simulate it in Excel, so you'll do this like once or twice for me, you'll never do it for the rest of your life, right? So because the Vensim or Insight Maker, it does this behind the scenes. So with Vensim, you'll draw a diagram which communicates to Vensim this expression. And then so Vensim will say, okay, the diagram you drew me, it translates into this behind the scenes, and then it then translates it into this behind the scenes. So we can actually ask Vensim to generate this output for us without us actually having to put any of the formulas in. So, so we start, our model really starts here, and then we also give Vensim a time step, and it does everything else for us. So, but we need to know what Vensim's doing, and that's why you're going to manually do this once or twice for me, and then after that, hand it all off to Vensim and Insight Maker. So when you manually do it, a generic or a generic system dynamics model is going to look like this. They'll all have these elements, where you got a time column where it marches on by dt every time step. Then we've got our stocks, and our stock variables accumulate over time, which means you'll have to put an initial condition into the stock variables and then formulas after that. But what the nice thing is that the formulas underneath each stock variable are always exactly the same for every single system. It's always going to be the value of the stock directly above plus dt times the sums of all the inflows minus the different so minus the sums of all the outflows. And so if you know which flow, you know which flow is an inflow, which flow is an outflow, like 1A might be an inflow into stock 1, 1B might be an outflow to stock 1, then you just take whatever this value is minus whatever that value is. If this is an inflow and that's an outflow, that difference gets multiplied by dt, and that's how you get from one cell to the next. And so the formulas for the stocks for every system are going to look nearly identical. What changes are the flows. So the flow of new bacteria, this is where the actual modeling comes into play. And so here, these are, whereas stocks have initial conditions in the first row, flows have formulas everywhere. And so the flow formulas, that's actually where you're modeling at every instant of time. This is how one state variable relates to the rate of change of another state variable. So this is saying like the inflow into stock 1 depends upon stock 1 and stock 2 in a formula you would put here. The outflow depends upon that in a formula you put here. The inflow and outflows to stock 2 are here, and so on. So this is where we actually do our relationships that we've been talking about in causal loop diagrams. This is where we quantify them as relationships between flows and stocks. And then if, in order to make the math cleaner, we can create converters, which are over here. We didn't use any in our simple bacterial example, but if we wanted to have some other quantities being used so that we could make the math simpler here, we could calculate those other quantities in a bunch of converters and then use those converters in the formulas here. And so as you're doing these examples in your homework, that'll start to make a little bit more sense, I think. So, so this is kind of our example with the bacteria. If I want to simulate birth and death for bacteria, bacteria are my stock. The flow 1A might be the inflow, which is what we already simulated. If I wanted to simulate death, then I would need to figure out, well, how does the number of bacteria relate to the outflow of bacteria? Well, in that case, as we'll see, if I know the average lifetime of a bacteria, that's effectively saying per bacteria, that's your contribution to the reduction in size. So if you know that you live for an average of L time units, then every bacteria has an outflow of 1 over L. So the whole population has an outflow of the number of bacteria times 1 over L. And that'll be what you put in this flow formula, so that you can then say that that every cell of your bacterial stock will be the previous bacterial stock plus dt times the inflow minus the outflow. So you'll actually get to simulate this, so you'll get some experience with that, like I said, in an upcoming homework assignment. And then, like I was saying, the converters can make things simpler. All right, so kind of bringing everything together, as I kind of hinted here, this is what we're going to learn to draw in Vensim and Insight Maker, these diagrams that have stocks, converters, and flows. Time step dt does not show up on the diagram. It's hidden in the software settings. So we normally, when we present these things, we usually have next to them, and you'll see Moorcroft does this, all of the formulas for your converters and flows, all of the initial conditions for the stocks, and then somewhere in there, you'll specify to your reader what the time step is. But the time step doesn't actually show up on the diagram. And this diagram is identical to this differential equation, also identical to this integral equation. So these are all 3 identical versions of the same thing. So we can view as stocks as taking integrals underneath flows. We can also view as flows of being rate of changes of stocks. But regardless of what mathematical perspective you take, this is the graphical way we depict those things, as kind of valves that affect flow rates into buckets. That's effectively what's going on here. And all of those things can be simulated in the same way using this methodical perspective that we show on the spreadsheet. And that's what Vensim and Insight Maker will do behind the scenes for you. All right, so questions about any of that? So right now, I just want you to kind of just sort of chew on that. And then starting in the next lecture next week, we're going to then work examples of simulating things like bacterial growth with death, and even like a toilet tank filling. And those will be kind of simple examples of an exponential growth loop, as well as a balancing feedback loop. And those you'll manually simulate in Excel, and you'll also then simulate them in Vensim or Insight Maker to see the difference. And that's kind of where we'll leave off before the midterm. And then after the midterm, we'll start building more complicated systems only in Vensim and Insight Maker. All right, so looking ahead, so this was lecture D1. So lecture D2 will be on Tuesday, D3 on Thursday, D4 on a week from Tuesday. So that's when the next chapter Moorcroft is due. So you've got about a week and a half for that. Insight Maker, it's a good idea to have it in your back pocket in case Vensim doesn't work out for you. So if you haven't created a free account there, recommend you do so. But if you're okay with Vensim, you can just stick with Vensim. And so another thing here, so your final project teams, it's still a little early to start really worrying about this, but start forming those teams. And so for those of you attending from remote and those in class, if you go to the final project information module, there's actually a spreadsheet there that if you click on, it's a Google Sheet, and you can put in like your name if you're looking for a team member, or if you would like to add a team member. So we're looking for nominally groups of 3 or 4. And then so it's just you don't have a deliverable due until I think after the midterm, but it's a good idea to sort of have that in play, because you're very quickly after the midterm going to need to tell me who's in your team, and then very quickly after that, roughly what system you're hoping to model. So those are the 2 deliverables coming up. In the shorter term, Sunday is the muddiest point assignment due, and there's a new assignment D1 that we'll talk about next week, but it will be due a week from Sunday. So if you're interested, take a look at that assignment. And then there's a kind of a complementary assignment that we'll talk about next week. And both of those assignments will be due a week from Sunday, not this Sunday, a week from Sunday. So one's kind of like a simple example, and 2 is a related example. And so they kind of like fit together, which is why they're due on the same day. So that's all we've got here. Like I said, midterm is not too far away. We basically, after Unit D, we'll have the midterm review. Actually, we'll have, the midterm review called Lecture DE, and then we'll have the stage 1 and the stage 2. So basically, after Unit D4, there'll be one more lecture, and then stage 1 and stage 2. And I think, I need to look, but I think this semester, this will be on a Tuesday and this will be on a Thursday. And I think that's it. So with that, are there any other questions? If not, then let me at least give you the attendance exercise, and then I'm happy. Yep. Yeah, right. So what I mean by coupled there is, as opposed to, just trying to get things organized here, is as opposed to 3 independent loops, like, you could imagine drawing a feedback loop, and another feedback loop that have no interacting variables. Then yeah, I'm just saying that I want to have a feedback loop that shares a variable with another feedback loop that shares a variable with another feedback loop. Yep. All right, so for your attendance exercise today, let me put the question I'll say here is, what term, and I'll give an example, stock flow converter, do we associate with the rate of change of a state variable in these models? So what term do we associate with the rate of change of a state variable? Is it a stock, a flow, or a converter? And otherwise, that's all I've got. Are there any other questions online that I can help with? If not, then I'll work on closing the room. All right, in that case, have a good weekend.